Hi everyone, I'm Harish Karnan, a PhD student from UT Austin. Today, I'm going to present our paper titled High Speed Accurate Off-Road Navigation Using Learned Visual-Inertial Inverse Kinodynamics. Let's begin. In this work, we are interested in enabling autonomous mobile robots to navigate accurately at high speeds in off-road environments. Consider a high-speed vehicle such as this one-fifth car called the UT Alpha Truck built at UT Austin, following a trajectory outdoors at high speeds. While at slow speeds, the car might be able to accurately follow the path. During high-speed navigation, however, environmental conditions like variable terrain can cause unexpected kinodynamic responses, such as wheel slip and vehicle drift, which may steer it off course, leading to poor accuracy of the traced path and sometimes might catastrophically damage the vehicle at high speeds. Here we see the UT Alpha truck traveling at 4 meters per second on slippery sand, experience significant drift, and when it switches terrain, additionally the change in friction might cause drastic effects. Here we see the Alpha truck autonomously tracing a circular route. We see that kinodynamic effects at high speed exacerbate the problem and throw the vehicle off course, causing huge errors. This is a major problem when we use classical controllers for high speed navigation. So now that I've motivated the problem, let's quickly look at the objectives of this talk. We will begin by looking at an existing approach to tackle this problem called Learned Inverse Kinodynamics or IKD models for accurate high-speed control. Specifically, we will look at IMU-IKD, that is conditioned on inertial information alone. We will then look at our proposed approach, Visual-Inertial IKD, that is conditioned on both inertia and vision. Finally, we will see experimental results that show the superior performance of VI-IKD compared to existing methods. To improve the accuracy of high-speed navigation, a promising approach is to learn an IKD model for control. Typically, an IKD model for navigation takes as input the desired next state along the path and the inertial observations to observe the kinodynamic effects of the terrain in the world. Since this IKD model is conditioned only on the inertial measurement unit to sense the terrain, we call it IMU-IKD henceforth. The IMU-IKD model shown here was successful at high-speed accurate navigation in off-road environments. However, in this work, we hypothesize that to enable accurate high-speed navigation, in addition to the inertial information of the past and the present, one also needs to anticipate the kinodynamic effects of the vehicle with the terrain in the future. There are two reasons for this hypothesis. First, the robot's physical hardware has electromechanical delays between when the action is issued by the controller and when that command gets executed by the hardware in the physical world. During high-speed navigation, this electromechanical delay causes the next action command to be executed at a future time step and at a future location, causing compounding errors. Secondly, an inertial sensor is capable of sensing the terrain only after the vehicle has traversed over it. So an IKD model trained only with inertial information cannot anticipate the future and might fail in situations where the terrain changes drastically as shown here. However, using an egocentric camera as a sensor would enable looking ahead at the terrain in the future. So an IKD model conditioned on such modalities can respond better by anticipating the kinodynamic effects of the terrain ahead of the vehicle. So towards addressing this problem, in this paper we introduce the visual inertial IKD model called VI-IKD in short. In VI-IKD, the learned IKD model F theta is conditioned on both the inertial information and the visual information of the terrain ahead of the robot. We represent the learnable IKD model as a neural network with convolutional and fully connected layers. The desired next state is extracted from a planner. The model is trained with data collected from our one-fifth vehicle, the UT Alpha truck with onboard sensors. The vehicle is made to execute random trajectories by teleoperating on varying terrains, and the VI-IKD model is trained with just about 20 minutes of real-world data. To extract the visual patch ahead of the robot, we perform homography projection of the camera's egocentric view into a bird's eye view and extract a terrain patch in front of the robot where the next action command will be executed. However, as we see here, the robot at time t is unable to see the patch due to a blind spot. To address this problem, we use the image frame from the previous time step. So here we extract the patch of terrain where the next action command will be executed by accounting for electromechanical delays. We repeat the same process for other time steps in the past by retaining a buffer and extracting visual patches of the same terrain from multiple viewpoints. We do this to encourage our VI-IKD model to be invariant to viewpoint mismatch. Here we see the patch extraction process running real-time onboard in NVIDIA AGX. The instantaneous camera frames are being translated into bird's eye view images and added into a history buffer from which a patch of terrain is extracted as shown in the green box, where the next action command will be executed. Now let's look at the indoor experiments. We compare VI-IKD against IMU-IKD and a baseline model predictive controller on the task of reference trajectory following at different speeds. The track contains 4 turns with 2 terrains, and shown in the black here is the desired trajectory. Here we show the trajectory traces for indoor experiments. We see that as the speed increases, the baseline approach in red performs poorly and sometimes fail to track the reference trajectory shown in black. In comparison to IMU-IKD at high speeds, VI-IKD is more accurate at tracking the reference trajectory. As we see here in this part of the trajectory traces for a top speed of 3.2 meters per second, VI-IKD in green is more accurate by being closer to the reference trajectory in black than IMU-IKD shown in blue and the baseline approach shown in red. Now let's look at some quantitative results. Here we show the Hausdorff distance of the trajectory traced by the baseline MPC approach to the reference trajectory versus the top speed of the vehicle. Here lower is better. We see that as the speed increases, the tracking error increases. IMU-IKD performs better than the baseline approach, and VI-IKD, our approach, performs the best among the three approaches. Here we show the results of outdoor trials. IMU-IKD as expected spins out of the trajectory when switching between terrains and gets terminated prematurely. However, VI-IKD, our approach, is able to successfully track the reference elliptical trajectory without spinning out and completes the task while being able to anticipate the future. I'd like to thank all the co authors in this work and I'd be happy to take any of your questions. Thank you for your attention.